In this series, we're going to explore structured concurrency, what it is, why it exists, and how Kotlin coroutines enforce it. But before we get to coroutines, we need to understand the problem they are trying to solve. So in this first video, we're going to talk about threads, the traditional way programs do concurrency, and why they quickly become inconvenient to work with. Once we see the limitations of raw threads, the motivation behind coroutines and structured concurrency becomes much clearer. In the next videos, we'll start introducing coroutine concepts like coroutineScope, coroutineContext, jobs, and context inheritance, and eventually see how all these pieces come together to enforce structured concurrency. Let's start with why using raw threads is inconvenient. One common problem is closing resources easily. Imagine the user opens up an app and it fires multiple concurrent tasks to fetch user details like feeds, notification, etc. But the user closes midway before everything loads. If it keeps on running, it wastes resources and we don't want that. Let me show you a demo. We're going to use threads, so if you aren't familiar with threads, here's how we start them. You call the thread and everything in the lambda is the task designated for the thread. You can start the thread by calling the start method. Now let's create a simple program that loads home page. I'll create a load home screen function and I will print loading home screen at the beginning and create 3 threads. The first thread is responsible for loading the profile, the second the feed, and the third loads notification. I'm going to start all of this thread by calling the start method. I'm going to wrap this load home screen in a thread. Although I'm calling this parent thread, it's wrong to call it parent thread because threads don't have a parent-child relationship. Once they start a new thread, their job ends and they do their own stuff. They don't care about the threads they started. For convenience sake, I'm calling them parent thread. I'll start the parent thread on main function, and after some delay, I'm gonna cancel the thread to simulate the user leaving. So essentially, we're canceling the thread that starts all of these threads. So ideally, if I cancel the thread that starts everything, everything should be canceled. All right, let's run it. And nothing happens. Threads don't automatically cancel the threads it starts. So this tells us that you have to manually track and cancel each thread on your own. I'm going to show you how that will look like. So strap in. Okay, first I'm going to remove all the code in load home screen. And we need to start writing some new code. Just like previously, we will create the profile thread. I'm gonna call the sleep function. The sleep function is a custom function that I created. This will try to intercept interrupted exception if thread sleep throws an exception. And we're setting the we're calling interrupt again. This will set interrupt flag on the thread. We will need this for later. For now, just ignore it. And we are checking the is interrupted flag. If the thread is interrupted, we print profile thread is interrupted and we exit the thread block. So we don't continue executing any of the work if the thread is interrupted. If the block executes everything, it will print profile loaded. So the thread completes its work. We start the other 2 threads similarly, just like that. We're calling sleep, we're checking is interrupted flag, we're printing interrupted, else we print loaded. and we starting all these threads. Okay, here's how we interrupt each thread. We're gonna put everything in try catch block. In the try block, we will join. So just like coroutines, join's gonna like block the thread it's running until it completes its work. And when it throws interrupted exception, we will catch. So any of this join throws interrupted exception, we're gonna catch it, and we will interrupt each and every thread. And as for why we're using current thread interrupt here, is because when the thread that's running sleep is interrupted, it's gonna throw interrupted exception. Because we catched it, it's gonna remove the interrupted flag. So we set it back. All right, let's walk through the execution. So first we called parent thread interruption. When you interrupt a thread, only that thread is interrupted. Its child thread are still running normally because threads do not propagate interruption. And this is the parent thread's task. It's running all this. It starts threads, doesn't care about what these threads are doing. In the try block, the parent thread calls join. The parent thread is blocked when it calls join, and it's currently waiting for its children to finish, right? But since we called interrupt, it is gonna throw an interrupted exception. So essentially, when a thread that is blocked in join is interrupted, the JVM immediately throws an interrupted exception. We catch that exception and we individually interrupt each thread. And when we interrupt these threads, the sleep will throw interrupted exception. And we check the thread's interrupted flag, and if it has that flag, we're gonna stop the work by just returning. This is a very roundabout way of canceling child threads. Interrupting a parent thread does not automatically stop child threads. We must detect interruption in the parent thread. We must manually interrupt each child, make each child cooperate by checking interruption and exiting. This manual propagation is exactly the complexity that structured concurrency solves. If you even forget one thread to interrupt, you are toast. Keeping track of threads manually is very tedious and error prone. So that's one problem. Let's see another problem. Imagine your program processes payment, and somewhere in this process, an error occurs. The thread that starts background threads isn't aware of errors happening in background threads it creates. It acts as if all the threads it created completed their work normally. This is very problematic. Let's look at an example that shows you this. I'll create process order function. This function will start 3 threads. This thread will charge payment. It will start and it will wait until it's completed before it moves on to execute another thread. So this thread writes to the database, and I am throwing runtime exception to indicate that database write operation has failed. This simulates a real-world failure where saving the transaction could go wrong. This also starts and waits until this thread completes its task. That's why I'm using join everywhere. And this thread sends a confirmation email. And I'm reusing the sleep function. Only catches interrupted exception if the sleep function throws. In the main function, I am printing processing order, and I call process order. And then I print order processed successfully. At least that's what parent thinks so. Let's run it. As you can see, processing order is printed and payment charged, and then an exception is thrown, and we can see the stack trace, and then confirmation email is sent, and the main thread prints order processed successfully. You might be wondering why this happened. Because threads are independent. The exception is thrown only inside one background thread. The parent is never notified and its siblings run as if nothing happened. The program believes everything succeeded even though the system is already in an inconsistent state. So this is very dangerous. Normally when a failure happens, you want to retry the operation or log the error, roll back the transaction, or stop the remaining tasks. But with raw threads, there is no built-in mechanism that informs the parent thread that one of its background thread has failed. Unless you manually implement communication between threads, failure can easily become silent partial failures. So with raw threads, you constantly have to remember every thread you start. You have to track threads manually, call join everywhere, and worry about whether some background task created even more background tasks. And when failure happens, handling them becomes even harder. You have to remember to handle every error where it occurs. If you don't, it silently fails. This will create bugs that are hard to debug, but here's where structured concurrency comes into play. It aims to solve these problems. Alright, that's it for this video. In the next video, we'll start looking at what structured concurrency actually is and the set of rules it introduces for managing concurrent tasks. So if you like the video, please hit the like button and subscribe. And thanks for watching.